Imagine if we can put our brains on a chip. Chips, not the edible ones, of course, but the ones that literally are in every single electronic device and gives it the ability to function. What? That makes no sense. Right now, your mind is firing a bunch of questions. I know it. How can this work? Why do we need to do this in the first place? It's probably a waste of money. Blah, 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 blah. I just thought that it's a fun, simple way to describe this new tech field that I'm super interested in. It's called neuromorphic computing. Essentially, all it aims to do is to replicate the energy-efficient capabilities of the brain to process and transmit information very quickly in the beautiful realm of computing. I actually wrote a review paper on neuromorphic computing, which essentially covers the major concepts of it and talks a lot about the recent advancements in order to make it portable and reconfigurable, while also eliminating the traditional computing approaches, so that the bottlenecks of the traditional computing approaches, so that ultimately it can thrive to surpass the conventional computing approach capabilities and just be the top level thing. I posted the link in the description box below, so please do check it out. I know, it sounds like a big mouthful right now, but take it easy, because I'm going to try my best to break it down in a very simple and brief manner. We're talking about the brain, the human brain right now, so we need to back up a bit and figure out how the brain works first. So, the average adult brain takes up space equaling to only 2 liters and operates at only 20 watts of power. And guess what? It's capable of achieving 1 quintillion floating point operations per second. It's so small, but it's so powerful. Our brain is made up of around 100 billion neurons, each of those having 100 to 1,000 synapses, which is approximately equal to a total of 100 trillion to 1 quadrillion synapses. To put this into better perspective, that's more than what Apple, the company Apple, is worth right now in the market. Think of it as a childhood game of broken telephone, but in this context, it keeps on happening over and over again, and it ensures that the message is reached safely and accurately to its destination, each and every time the communication between the 2 neurons happens in the synaptic cleft, so in the synapse, basically. If we can somehow mimic how the brain works, hint, hint, the basis of neuromorphic computing, it will completely revolutionize how the computing realm works altogether. This will take us to new heights for leveraging emerging technology while also being sustainable and cost efficient. Okay, but why not supercomputers? Aren't they very powerful? Well, if we try to mimic the behaviors of neurons and synapses in modern-day supercomputers, it will require more than 1.5 million processors and over 1.6 petabytes of high-speed memory. This basically means that it will lead to an intense amount of power consumption, and entire buildings will be needed to house them. Every computer in the world is based on the von Neumann architecture. This essentially runs on binary codes, your favorite zeros and ones. The key bottleneck, however, is when it comes to the memory and the CPU component being 2 separate things, which basically requires more time and energy to send information back and forth between each other. But in the brain, it's totally different. The memory and the processing systems are literally in the same place. Now we can finally stop at neuromorphic computing. I really hope that you guys enjoyed the roller coaster ride and felt the thrill of the synaptic gap. A neuromorphic computer has three key components: artificial neurons, artificial synapses, and memristors, which are all fabricated on a chipboard to mimic the structure of the human brain and allow the processing and memory to occur in the same place. Here's the gist. Artificial spiking neurons are designed to emulate the behavior of a biological neuron. Self-explanatory. They receive input signals from other neurons and they generate output signals in the form of spikes when their internal state reaches a certain threshold. Memristors, on the other hand, can actually change their resistance based on the surge of voltage. So that's basically like the electrical signal it receives, and this basically allows it to remember its previous resistance states. So it's very similar to that of a resistor and a transistor. So it's more or less like the combination of a resistor and transistor, but like the next level. And they can essentially store information even if the device loses power. So think of it as like a chameleon. So chameleons change colors, like different colors, and it can also remember the color that it had changed to previously. And finally, we have artificial synapses, which essentially connects artificial neurons, just like how it's done in our brain. So just like how in between the two biological neurons, there's a tiny synapse similar to that. When I was researching, I came across this super cool guy. His name is Jiwon Kim, and he's a professor at the MIT. So essentially what him and his team did was they put forth a lot of research into developing a scalable, reconfigurable, as well as portable neuromorphic chip, which essentially works by like having many layers stacked on top of each other like Lego blocks. And so they first, to create this, they first went about designing the artificial synapse hardware, and later they figured out how the memristor is going to work. And now, recently, they have developed a portable neuromorphic AI chip device. They're currently looking into how they can shrink the size of this chip even further, making it more portable and accessible to everyone. And I think there was this article where they said that they were thinking of incorporating this into biocompatible applications, so like electronic skin, like chips on your skin, if you've ever heard of that, but I'll probably do like another video on that later. This I talk a lot more in depth in my review paper. You want to hear another cool fact? Well, so far we know that neuromorphic chips can process a whole lot of information very fast and sustainably. Actually, it's a buzzword for developing specialized hardware and software that can accelerate AI algorithms and can make them more energy efficient. So this, what I'm telling you right now, basically means that this piece of technology can be used to train AI models that can constantly learn and adapt to real-time situations, environments, similar to how our brain is constantly learning and adapting to new information all around us. There's literally so much talk about AI nowadays, and it's crazy, mind-blowing how this tech can literally take it to the next level. The potential for neuromorphic computing to disrupt the way we design computers and process information is very strong, if you have not understood that by now. And it's really exciting too, because they can eliminate so many problems such as the von Neumann bottleneck, carbon footprint dilemma, processing large AI algorithms, and allowing them to train and adapt very quickly. This literally can have a very wide impact, because if you think about it, we use chips a lot. Chips are literally the fundamental components of the electronic devices we use every single day. Like for me, for example, right now I'm using my phone to film this video, and the phone has a chip inside of it. So just count how many electronic devices that you use every day, and you'll know the demand for this technology. And literally, if this trend keeps on continuing in like emerging technologies such as AI, AGI, edge computing, brain-computer interfaces, and automotive vehicles, literally it's gonna light up the future and improve the quality of life for all human beings, and also enable us for new, better discoveries. Well, now I guess putting a brain on a chip is, after all, not that bad or insane to think of.